I'm here today to share with you the result that we have got so far about Pantheon. Pantheon is a project that has been funded within the H2020 program. It's about precision farming of hazelnut orchards. I am the coordinator. And this project is a consortium composed by 4 universities. We have University di Studi Roma Tre, from which I come from, University di Studi La Tuscia, Université Libre de Bruxelles, University of Trier. Then we have a large enterprise, which is the Ferrero Trading Lux, and a small and medium enterprise, which is the Sigma Consulting that is located in Rome as well. So just a few words about myself. My background is on control and robotics. I've been dealing mostly with theoretical questions about multi-robot coordination, how to optimize the topology of multi-agent system, and how to do distributed algorithms that can be provably able to estimate something. And there's an example of a coordination paper that we wrote a long time ago. So today we'll be talking about hazelnut orchards, and I believe that the best things to do is to spend a few minutes telling you what I didn't know 2.5 years ago, which is how modern hazelnut farming is carried out. So the first thing that you can notice when you look at a hazelnut orchard, it's quite easy, is that the regularity of the planting pattern. Clearly, having a regular layout helps a lot for the mechanization of many field operations. However, there are still several operations that are either labor-intense or time and resource-consuming, and those are, for instance, the control of the irrigation in terms of regulating the irrigation, or the control of suckers and the pruning practice, control and pest and disease, and estimation of the production. Now, without going too much into the details, I just want to make the main point. For instance, for what concerns irrigation, it's quite automized in the sense that you have systems that are already deployed in the field. However, to decide the level of the irrigation, what happens is that weekly, the agronomists have to go there and figure out which one is the right amount to water to irrigate. Similarly, if you want to deal with the management of the hazelnut tree, I figured it out when I was speaking with agronomists when we wrote this project that this kind of tree is quite interesting because it would grow as a bush if you didn't treat it. And so for the sake of the production, they want him to grow as a vase shaped. To achieve that, you have to do pruning and sucker control, okay? Pruning is something that is achieved either manually or through tractors, and so it depends whether the tree is young or adult or the orchard is small or big, large. But anyway, you do not have control over the shape that you achieve or things like that. Well, what concerns suckers, those are treated mostly when they are in the juvenile stage through the administration of herbicides. And what is interesting here is just to point out the fact that you do not have a way to distinguish whether that plant really needs it or not, or if it needs it, how much herbicide should be sprayed, all right? Similarly, the same thing can be said for pest and disease control. What happens is that the orchard is inspected regularly by the agronomist, and the idea is that they normally consider the orchard divided in sectors. For each sector, you select a few plants, you analyze those plants, and you say the rest of the sector will be pretty much the same. That's the approximation that is done. And in this way, also what happens is that the treatments are homogeneous. It's actually interesting that the product estimation is carried out by going to the field, counting on some selected branches what is the actual production, and then making a projection towards the production of the whole orchard, all right? So if we want to try to draw some summary about how current best practice is carried out, the idea is that basically you just observe a few plants, and then you do homogeneous treatment, assuming that in the same sector, everybody behaves the same. Clearly, this is not an optimized approach. What happens is that you might have a waste of production that induces an economic loss, but even worse, you might have avoidable pollution from which environmental damage is generated, right? What we want to do in this project, we want to have a complete shift in the paradigm, and we want to be able to achieve the resolution of the single plant, both in terms of collecting data and performing a farming operation. Clearly, if we are able to control every single plant, it means that we should also be able to detect promptly per plant limitation and then react accordingly with focused intervention. As a result, we should be able to increase the production because, in average, the health state of the orchard should improve. We should be able to have a more environmental friendly management, as we should be able to reduce the waste of resources and also reduce the uses of chemical inputs. And we should be able to reduce the human burden, especially on large-scale orchards, where certain activities cannot be carried out at the moment, when it's really on a large scale. Now the question becomes, that's another point I want to make. We have, I always say, we didn't want to sell that we would go to the moon. Like, we wanted to follow a very pragmatic approach, which means we sat down with agronomists of Ferrero, and we asked them, what do you really need in the field? And then we compared their needs with what could, with current technology, be achieved. And we figured it out together that we could have focused with the hope to achieve good result on the following set of points: on the estimation of the phytosanitary status of the plant, on the regulation of the automatic irrigation, on treatment of suckers, which is a big deal for those kind of cultivation, on the improvement of pruning practices, and try to, I say try because this is the one that personally I think is the most complex, try to render the estimation of the production automatic, okay? So the question becomes, how did we, or how do we expect to achieve this goal? Our idea, I like to sell it this way, is to try to propose what would be the agronomic equivalent of the supervisory control and data acquisition system, which is a standard de facto in the industrial setting, all right? So the SCADA system for agriculture that we envision is composed by a bunch of ground robots and aerial robots that move around in order to both collect data and perform agronomic intervention. We also have supplemented those robotic availability of presence with an IoT agrometeorological network for environmental monitoring. All the data is fed into a central operative units where the data is treated, integrated in order to figure out what should be the next agronomic intervention to be carried out, perhaps autonomously by the robot. And also this will provide a decision support system for the agronomists, okay? Now, we are halfway through. The project started 2 years ago, and we built the SCADA system, and I want to spend just a few words to tell you how this works in practice. The main components are a wireless network backbone, because the robotic units will work under ROS. ROS has been already mentioned here, so I don't have to spend further words on that. We have the ground robotic platform, we have the air robotic platforms, we have the IoT that I mentioned before, and then we have the software architecture that somehow puts everything together as a glue, all right? So for what concerns the wireless network backbone, the first thing that we realized when you leave the lab is another word. You're used to work in your lab, everything works fine. The first problem is like, for instance, even just electricity is not so obvious that you can have it. You cannot take anything for granted when you go in the field. That probably most of you guys know better than I do. So what we did, we needed a place where we could store the actual local farm server. And this happened in the warehouse, which is, I have to cut the pictures because it's almost like 1 kilometer away from the actual field. And so we had to find a way to have an interconnected system, and we used a 2 long-range antenna, point to point, that goes from the warehouse to the, I don't know if I have a laser pointer here, no, it's fine. From the warehouse to the field. Over there in the field, we have a wired antenna to the mesh, to a mesh antenna. In this way, you can have we have deployed several mesh antennas. We created a Wi-Fi network over which data can be carried, and the robot operated system can work through the robots, okay? For what concerns the robotic platforms, we have started from 2 commercial products from Robotic. Those prototypes share a common sensorial equipment for what concerns localization, navigation, and safety, clearly, because this would simplify our design. And then they have been specialized, customized for the dedicated precision farming activities. We have called them Robot RA and Robot RB. We didn't have that much fantasy, I guess, about that. Actually, this was mentioned. Like, you could have been a little bit more, imaginary, but that's okay. So Robot RA is the one that mostly will be collecting data. He has a robotic arm, a lot of sensors. We discussed about that. While Robot RB is the one that will be mostly focused on agronomic intervention, because it's the one that will be spraying herbicides to suckers. Okay? So for what concerns the ground robotic platform, the sensorial equipment that they will be used for the collection of the agronomic data is a LiDAR. The LiDAR will be used mostly for the 3D geometry reconstruction and for sucker detection. Actually, for sucker detection, it's more like to have a ground truth, because it would be a little bit too expensive just to do sucker detection, but it's a good way to see whether what we are estimating with some other sensor is sufficiently good, because the LiDAR gives you a very good resolution. The multispectral camera will be mostly used for fruit detection and pest detection. Actually, we just realized that also for sucker detection can turn out to be convenient. And the RGB camera would be used mostly for threat detection and pest detection. For what concerns the aerial robotic platform, we have been using a very standard platform, which is the DJI Magic 600 Pro. As I said, we wanted to be pragmatic. If there is something that works well, we don't want to reinvent the wheel. We are using it and try to integrate everything together. We equip this with a ruggedized onboard computer. There is a differential RTK GPS system for the planning and the navigation. And for what concerns the payload in terms of agronomic sensorial equipment, we put what I think is quite standard for this kind of operation. We have a multispectral camera, a thermal camera, and a RGB camera. The first camera will be used mostly for production capability and disease detection, thermal camera for water stress and disease detection, and the RGB camera from production capability, okay? As I said before, we have supplemented the fact that we have robotic platforms with an IoT. The difference is mostly that while the robotic platform will be intermittently on the field, the IoT will be constantly sending data to have some information about environmental conditions, okay? And the components are the weather station that has been used for sensor, has been and will be used for sensor calibration and product estimation. And then we have soil moisture and soil temperature sensor that will be used for the analysis of the water status. Actually, just last week, we presented a paper that we just discovered awarded as the Young Award Best Paper for the modeling of the soil plus the plant as a dynamical system with a spatial resolution and with an intermittent extended command filter. The ratio, the idea is that we don't want to put a sensor for each parcel of the soil, but we want to use an observer in order to estimate the state of the water content in the plant and the water content in the soil without having too many sensors placed in the environment. So if you're interested about those kind of things, send me an email. I will hook you up with the students, and we can discuss the things together. Okay, so to close it, the software architecture, as I said, there is ROS. Actually, as I said before, ROS is meant to serve the robotic platforms, while we also have an IoT. So we made this design decision to decouple the two networks because the IoT works on a LoRa network. It's low consumption, low bandwidth, but it's the best solution to send over time, continuously over time data. While the Wi-Fi networks is going to be used only when it's needed. They are both solar powered, so they're autonomous also because, again, bringing electricity in the field is not something that easy. And now, just a few words about where the experiments are going to be taken and has been taken so far. We are using what is called the Azienda Agricola Vignola, which is in Caprarola, Italy. Province of Viterbo might not tell you that much, but 80 kilometers away from Rome might help a little bit better. And also this 80 kilometers means that we have to drive back and forth every time. The logistic of the project is not the best that could ask for, but you know, in Rome there was no field, so that's the only solution to do that. We have pretty much 16 hectares. So we mostly did the experiments on field 16 and field 18, that is overall 12 hectares, where we have two different varieties of hazelnuts. And mostly the thing that is most important, rather than the variety, is the fact that one is an adult orchard, while the other one is a young one. So the agronomists are very happy because they can try all their stuff with the fact that those trees are still young and they are growing. From my point of view, it's just robot that has to go through, and then for me it's pretty much the same thing, besides the fact that on the adult RTK GPS doesn't really work that well. And so you need to supplement this with a good filtering approach. Now it's time to talk about what we have been doing in these 2 years. So to just give you the timeline, the first year has been finishing the design of the robot, having the robot to work on the field, seeing that things didn't go very well, sending the robot back to Spain, having it fixed, coming back. So the first year was design and prototyping analysis. In the second year of the project, we were able to start to do something. And the thing that we have been doing in the last year, which was the second year, was the design of a proper navigation architecture for the Ackerman vehicles, a SLAM algorithm that was tailored for hazelnut orchards, some motion strategy for data collection, and an approach, a framework for the control of the hazelnut, okay? Well, this is a video in which you can see that if you don't do maneuvers properly, due to the fact that the intra-row spacing is quite narrow, you will get stuck. And that's just to motivate the fact that you need to have a robust navigation system that take into account the features of the environment in which you are moving. In our case, the fact that the layout is quite regular, the terrain might be uneven, and there might be a narrow intra-row spacing. That thing over there was for the robot. It's not used by the robotic one, the tag. It's just, it was part of the video, and that's it. Okay, and the features of the robot, which was an Ackermann kinematics. For those who are not aware with Ackermann kinematics, you can think about it as a car-like vehicle, and the mechanism is thought in such a way that the goal is not to have slippery phenomena when you are trying to move on a trajectory around a curve. That's the mathematical model of it, and that's all we have to know. And for what concerns the actual navigation stack, every piece of code that we have developed and that has been sufficiently tested is online, is available. We love that you have to share it with everybody. Also, the data that we collected is partially already online. It will be fully available online once we have finished all the things that we have to do. And there is a repository. Whoever is interested can just talk to me and we can share everything. And for this navigation stack that we developed is composed by two components. Funny enough, we tried to see whether we could find something already developed in ROS. For what concerns Ackermann vehicles, I haven't found that much, so we decided to do everything on our own. And that's why we developed this real-time local planner. We found just something with elastic band, but we didn't like that much how it behaved. And so we did this piece of code. And our navigation architecture is composed by a real-time local planner, which is coupled in a feedback way with a post-regulation control law. We kind of use a different approach. People normally do trajectory follower, but since we realized that when you move in the field, you move from one pose, meaning from one configuration to the other, to collect data, perform a certain intervention, we thought that the best solution for us was to discretize the trajectory and just do post-regulation as a control law. How does the local planner work? Well, the idea is very intuitive. We are trying to generate in real time an optimal, in some sense, collision-free trajectory for this kind of kinematics. And the way we achieve that is by reformulating the planning problem as an iterative constraint minimization problem of a finite horizon. And the outcome, as I said, is a trajectory which is represented by a sequence of discretized pose configuration. Pose simply means position orientation of the robot that you want, okay? Now, that's the mathematical formulation. I don't want to go that much into those details. There are only two things that, in my opinion, are interesting to be shown. But among the constraints, we have this dot Q, which means we are taking into account the fact that kinematics is an Ackermann, so that the trajectory will be feasible for that kind of kinematics. And we also put in the constraints the fact that we want to always stay on a minimum safety distance from the obstacles. And that's it. That's the only two things that really matter in this slide. That's the outcome in a simulation. What we have, we clearly have also experiments. In this simulation, you can see that the robot is planning over a finite horizon, a trajectory towards a desired goal. In the way forward, there is no obstacle. The obstacle is basically the dynamite that the student put down there. And on the way, on the path backward, you will see that the dynamite will intersect with the path, that with the trajectory that has been planned by the robot. And so the robot that sends it has to dynamically replan the trajectory. You can see now that the dynamite is hidden in the tree, down is moved over there, is actually exactly on the path, and the robot, when it sends it, he has to replan in real time. As you can see, the computational cost, that's in microseconds, is quite good. We have a spike only when there is the detection of the obstacle, and the explanation is simple. Once you have a trajectory, even if you replan over a finite horizon, if you don't meet any obstacle, the replanning is cheap because you don't change that much the trajectory. You might have a spike when you have to make a serious effort to replan the trajectory. All right? Now we have the planner. Now we have to focus on the post-regulation. I told you before that the planner was giving us a sequence of configuration where we wanted the robot to be. And now we need a low-level control law that moves us from one desired configuration to another one. Without further ado, we can simply say that we consider the bicycle as the equivalent kinematical model of the Ackermann, we do some coordinate transformation, and we do a no-smooth control design to have a no-smooth control law to solve this problem. And we have been able to formally and experimentally validate the correctness of this approach. Regarding the coordinate transformation, again, without going too much into details, the state variable becomes this rho, gamma, and delta. You can see that if those variables go to 0, the initial configuration will overlap with the final one, which in practice means we have reached the configuration we wanted. That's the only part that we should care about. That's the no-smooth control law that we designed with the sign function. And that's a video in which there is no planning whatsoever. We just said start from a configuration which is hidden behind the tree and go to a final configuration which is somewhere over there. And that's just the control law doing its job. Now, by coupling the control law and the trajectory generation, we are able to do something much more interesting, which is moving in more complex environment, as would be moving from one row of the orchard to the other one while avoiding the obstacles. Okay? In the video, I would focus on the video on the bottom, even though now we have to start to wait that it restarts, because the thing that I want to point out is that in the second case, we simulate the presence of a dynamical obstacle that suddenly appears, and as you can see, the trajectory is regenerated in real time, and the robot follows another path. In this way, we couple controller and planner in a feedback loop. Okay? Now, so what we have got so far? Well, now we know how to move from a point A to a point B. That's fine. But what is the point A? What is the point B? Where am I? Meaning that we need to couple this navigation stack with the capability to understand the environment surrounding you. And so the next step was building what is called simultaneous localization and mapping algorithm that would provide us with a knowledge of the robot in the world, in this case in the orchard, a knowledge of the orchard itself, and perhaps, as I will describe later, also an estimate of the planting pattern, which is the regular layout of the orchard, which will turn out to be useful to distinguish mostly between a dynamical obstacle and what is supposed to be a tree. Okay? Again, everything in C++, ROS, open source, available to everybody. Just contact me, and we can share everything with you. Okay? How do we work with that? We use Velodyne and Wilson encoder for now. Actually, this is not exactly correct, because then by the time I made this slide for another presentation, and today we also integrated GPS, MU, and everything else, as you will see in the video. So this slide should be redone. Okay. But what is interesting is that we developed yet another extended command filter for SLAM. I would rather say that we tailored the standard SLAM algorithm for the features of the environment in which we are moving. And we call this H2O SLAM, that stands for hierarchical orchard, hazelnut orchard SLAM, in the sense that we have two components. We have the H2O SLAM that builds map and robot pose for the hazelnut orchard, and we have another EKF that is in a feedback loop with this one, that is the HOL EKF that estimate the planting pattern of the orchard, meaning that we know as a priori information that there should be a planting pattern. We don't know what would be like a 4 times 5, 3 times 3, and then we estimate that. Okay? Now, the HO SLAM follows a classical EKF approach in which we have prediction and correction. I also emphasize the innovation step, in which this is where we made something that was tailored for our setting, the hazelnut orchard. We have the Ackermann kinematics, as I said before. Clearly, this could be substituted with a unicycle, point particle, something more complex, whatever you want, and things should be working. We model the map as a topological map, which is the thing that makes more sense in this setting, also because you might want to scale up with respect to the size. And so you build just a graph in which vertices are trees, landmarks, with an ID that represents their code and their position in a global reference frame. Okay? Now, for what concerns the prediction, the only thing I want to say about that, the prediction is meant to give you an idea of what the robot would be next, assuming that you have the kinematic robot model of the robot and a knowledge of the input to the robot. Then there is the innovation term. The innovation term, I would like to sell it in this way. It gives you a measure of how accurate is the current estimate of the map and the current estimate of your position in the map. And how is that achieved? Well, comparing what you observe with what you would be observing if you were where you believe to be in the map that you have built so far. That's a 10 in English, I guess, at least this. Okay. And once you achieve that, you make this difference, there are two components that are really important. Important in our setting, which is, again, a hazelnut orchard for those who haven't got this, that have been repeating for 10 times every slide, I guess. The tree detection and the data association. So, tree detection. Tree detection, we at the beginning said, oh, it will be easy. There are just the trunk of the tree, and then we would be using the SIC laser that are on the top left and bottom right corner of the robot, so that we have a 360-degree coverage. I couldn't be more wrong than that, because the position of the laser was exactly the height of the grass. So the only thing that you see is a lot of noise. We didn't have this issue in the lab. We realized that when we were in the field. Say, okay, SIC, cancel. Doesn't work. So what do? Well, we did something, I guess it was intuitive. Okay, we have a LiDAR. We wouldn't be able to see what is back now, but if we move forward with the LiDAR, since the LiDAR in our case is a Velodyne, which has 16 planes, they call them rings, so from now on is going to be a ring. One of the rings will be pointing to the sky, and what you sense over there, it's at most the canopy of the tree. Then we use that sensing to define a region, and then we project down this sensing region to a lower ring that is closer to the height of the trunk, and then we clusterize those points in order to have an estimate of where the trunk could be. It turns, as you will see in the next slide, it turns out to be quite robust and works very well. You can make this, you can trick it the way you want. You can add the number of layers, you can add the number of rings. It's just a matter of computational burden. 2 rings seems to be sufficient. They work reliably, and that's what we are using right now. And now, the next step is the data association. The data association is based on a heuristic algorithm that was developed by one of my students when he was doing his PhD, not with me, I got him after. We took his work and we modified it again to modify in the sense we tried to improve it to tailor to the setup that we had, because again, we are going to move on as an orchard. That's where we care to have a certain resolution, right? So the first step of the data association is quite obvious. By the way, a data association, for those who do not know this, simply means I'm observing something, which tree in the map I'm observing is part of the map already, is a new tree, okay? So the way in which we do the data association, the first 3 steps is what is called gating, which means if this is the measurement and this is your knowledge of the tree, and there is too much of a distance between those 2 things, there is no data association for those 2, for this pair. Then we make another obvious observation. For each tree, there must be at most an observation. And then for each observation, there should be at most 1 tree, right? The thing that we add is that observations should somehow match the planting pattern that we have in the hazelnut orchard. And that's where we made our improvement, because we developed this HOL EKF that, based on the map that you are building and refining, it also gives you an estimate of the planting pattern that is refined as well. And the way in which we do that is quite intuitive, I guess. We define a direction that we call along the row, the X direction. Then we define a direction which is called in between the rows, which is the Y direction. And then we have an angle, which would be, that's something I will tell you double. And then we need to clearly have an estimate, once we have understood in which direction the row goes, of the step between one plant and the other. And then we call this the distance along the row. The same happens between the rows, and we call this the distance between the rows. So the algorithm, the EKF algorithm that estimates that, what it does is quite intuitive. It has a state composed by 3 variables, which is the delta x for the step in the x direction, the delta y for the step in the y direction, and then there is an angle that simply represents the rotation of the planting pattern with respect to the GPS coordinate reference frame, okay? In this way, we then develop an algorithm that, starting on the observations that are taken over there, detect pairwise neighborhood along x, along y, compute the average distance, and then using this information, you compute an inversion term, and you update the planting pattern as you would be with any other EKF algorithm, okay? Now you have sufficient information to carry out the correction step of the main HO SLAM algorithm, in which you tend to improve the accuracy of both the knowledge of the environment and the location of the robot, okay? Clearly, if you realize that what you have been observed doesn't match with anything that is already in the map, but still reflects somehow the fact that it looks like it's in the intersection of the grid, this might be a new tree, okay, add it in the state vector of this SLAM, okay? Now, this is, I had to speed up because otherwise we would be there spending a lot of time. This is an overlay of the outcome of the algorithm with a map taken from Google. And as you can see, the algorithm seems to perform quite well. All the trees are well detected. This is real data. It's a bag computed on rows, and then we run the algorithm over the bag information, and then we overlaid with the GPS map, with the Google map photo. And as you can see, it seems to be doing its job, it's reliable, it does what it has to do, and that's, for what we need, that's enough, okay? Now we know how to move in the environment. We have a good knowledge of the environment. It's time to do something useful for the hazelnut orchard, I guess, okay? And we start to question, how do we collect data? I would, as a researcher, normally I can do so many cool things. It ended up to be just a simple go back and forth because it seems to be the best strategy, unfortunately. But then the question became, okay, at least is there a good way to analyze where and how to collect data with respect to a tree? We did some research on that. Also in this case, it seems that the best solution is to have 4 points equally spaced around the tree so that you can take the shots from different configuration. You maximize somehow the information that you are collecting. And that's what we ended up doing, okay? In particular, with the LiDAR, we collect from each of the locations that were in the previous slide, P1, 2, 3, and 4. We collect one scan with a LiDAR. We collect six pictures with the cameras, RGB and multispectral, in such a way that we can reconstruct this pseudo-panorama RGB image composition as in this slide that is going to be used by the guys in Trier to do their stuff, to find the vegetation index, all those things that are so cool, but that's not my word. And this is an example of how the data collection works. I'm not going to spend too much time on that. Basically, we have this robot that is stationary in the middle of 4 trees. In this case, the arm doesn't even go up. Basically, we first collect the data with the LiDAR, then we rotate the arm in such a way that the 2 points are kinematically related, and then we get the data from each configuration. We take several shots with the other 2 cameras, okay? This is an example of the outcome that you get. This is the raw data coming from the LiDAR, plus some treatment that the guys from Trier did on the data. In this case, for instance, this is an heat map, while this other one, I was told, is a classification. Green is soil, then yellow becomes vegetation, and so on. And what is interesting here is that clearly, this was fun because as a roboticist, localization accuracy for us has a certain meaning. Low accuracy in position for people that do remote sensing has a complete different meaning, right, in terms of the resolution. And so what happens is that what you get clearly with the localization approach that we have is not sufficiently exact to align the images, and that's something that is obvious. However, what they were able to do by figuring out some characteristic features of the tree, they were able to align the scans. This is, by the way, real data coming from the young field. Young just because it's easier to visualize with respect to the adult tree. We can do clearly the same also for the adult tree. And in this case, you can see that before the alignment, there is a mismatch from the scan taken from the 4 points, but then you can do an alignment, you get this, but even better, after some treatment, you get this 3D reconstruction of the tree. And from this information, we move to this other one, in which we do some filtering until we get to what we really care, which is the 3D structure of the tree that will be used later on, meaning starting, I guess, next month, to develop some pruning algorithm. We are working with agronomists, try to translate everything the same word in a pseudocode that might work fine for us. We are actually, this is interesting because this is obtained by a tree with the leaves. So we didn't have the time to check how accurate was this modeling, but right now we are collecting. You will see in the last slide, I got a video 20 minutes ago from students that were on the field. We have a very new and fresh video in which they went back to the field. Now trees are naked, no leaf, and they went to collect again the LiDAR information to have the actual 3D structure, and then we will be doing the comparison in the next days. Okay, so let's move on the sucker management control. As I said, sucker for those kind of plants is the most complex part, because since this tree tends to grow as a bush, suckers, as the word says, suck the energy of the tree, and so you need to treat them, okay? Talking with the agronomist and being an engineer is a funny dialogue when you start talking, but after a while you get along fine and you find the solution. We try to say, okay, what would be features that we can use to make an algorithm to regulate the herbicide out of it? And we realized that something very simple and probably effective, I say probably because clearly we need the next season to test it, because another problem compared to the lab that there is also the season for the vegetation. So you develop something now, you stay like this until the plant is ready again. So we have developed this algorithm in which we, based on the estimation of the volume of the canopy, we regulate how much herbicide to spray so that we can give a proper treatment for each single plant. It works simply by assuming that you have a proportional quantity as a function of the quantity of herbicide as a function of the volume of the sucker. Now, I gave this to a close friend of mine who does computer graphics research, and he put this hand in the hair because he said, when you work with open air vegetation, it's a mess. He was right. All the algorithms that the state of the art do not work right. You can see that the point cloud coming from the Velodyne, and you can see what a standard algorithm would do. A meshing algorithm, nothing basically. And so we said, okay, we need to do something different. Let me say in advance, we are now shifting a little bit the direction because we want something even better. But the first way in which we approached the problem was, can we solve this problem by not adding any additional sensor to what you already have for the sake of navigation? Meaning, can we use the Velodyne and a 40 euro camera attached to it and kinematically tuned, okay? The answer is yes. It's not great, but according to the agronomist, it already works fine. The problem is that the Velodyne is a LiDAR that you use to avoid to bump into obstacles, not to do 3D reconstruction of surfaces. So meaning the resolution is low, the number of points that you get is not that great, but that's just the detection that we use a neural network, YOLO, as pretty much everybody else. We use RGB. We realize that we can do so much better, make this so much more robust using some spectral indexes I will show in this last slide, and that's what we are doing right now. But that's the algorithm that we developed by hand, and the idea is that you get a bunch of points that are pointless somehow, but if you have a priori knowledge about what you're looking for, which is a sucker, is like a rooted graph, you can develop an algorithm by which you can estimate a shape, and as you can see in this slide, this is the real shape. This is what we reconstruct. And we do, I would call this a preliminary because statistically speaking, 4 data sets are not that much to give a result. But what we did, we use Archimedes approach. We cut the sucker, we put in the water, we compute the volume, and we compare with what the algorithm gives. The algorithm gives an error, which is around 21% of the error above all. We saw overestimate at most 21. Agronomists were extremely happy. As an engineer, I know that if I use something else as a sensor, I can do even better, but for them this was already a good solution. Last slide. What we were doing here is realizing that if instead of using an RGB as a plain image, we do something a little bit more complex, which could be as simple as computing the excess green index, since the sucker has a different emittance than adult leaves. This makes the YOLO network more robust, and we can make the old detection more robust, even though it already works, I have to admit, quite well. And just a minute for me, I'm organizing an invited session for precision farming at the Conference on Control Technology Application in August in Canada. Montreal in August is great. If you want to submit something, please send me an email. I will tell you all the information about it. Thank you for everybody for listening. Thank you to the crew of the project. Thank you for my guys that are always on the field. And that's the video that we got today. So if there is any question, we can see the video in the meanwhile with the naked tree.
Thank you.
Did I make it?
You finish just at 25. Perfect. During the commutation with the next presentation, maybe we have time to take just one short question. Yes, please.
Sure.
Why did you use were you processing real time?
Yes. And I mean, I have to admit, YOLO is not my word, but I have these great students that has a lot of experience. He was part of the another important European project, Flourish, that was before. Now I got him, and PANTHEON is jumping from one project to the other. He had a lot of experience. He did that it would work well in real time. As for what he told me, is basically sampling from the video a picture at certain airs, and it does the analysis over that.
How many images did you have to live?
The labeling part,
How many images were
you know what? I have to ask him. I don't know the answer to this question. I know that they have been suffering with the labeling a little bit, meaning that it took a couple of days to do the labeling, probably.